Okay, hello Daniel, Abdi, and Ian. Hope you guys doing well. So I just want to mention a quick things. So one important message that Dr. Kasan wants uh, me to remind is for lab number 3. Each student need to come up with 2 design, and they both design need to be works. Okay, they both need to work. So it cannot be one works, one not works. So when they do the designing, they should think about 2 way of designing. Obviously, most likely one will be 318, LM318. The other one will be LM741CN. So for lab number 3, I just want to briefly go over it. I know you guys definitely understand it, but I just want to go quickly. So for lab 3, you can see it. We have this LM741CN to start it. So for the first part for this one, what you can do it is, okay. So if my R is assigned to be say 1000 K, my ACL is minus 1000 K over 10 K, which is minus 100. My gain will be minus 100 volts, V to V, right? My closed loop frequency minus 3 dB is equal FT over 100, which is 1.5 mHz over 100. Okay, is 12. Okay, that is given here. Okay, the FT is given here. So I got my FCL is equal 15K hertz. Okay, that's the first thing I get, FCL. All right, the next things we have is for the part 2. As you can see, VI, if given you the input voltage to be 100 millivolt peak, okay, sine wave, what is FM? Okay, so we need to find FM due to the slew rate. So if again R equal 1000 K, okay, VO peak is equal VI peak times ACL, which is times 100, right? So you have 100 millivolts times minus 100, so which we will have minus 10. Okay, V peak. But obviously, you know, the negative is not really important things here. Again, SR, O, okay. So the SR we get from the data sheet is SR is equal to 0.5 volt per microseconds. This you can find it in the data sheet of the 741 slew rate. So all we need to do is slew rate to check it. As you can see, it's given here 0.5 volt per microsecond is given in the 741 data sheet, and same thing for 318. They both provided on the lab sections of the our Dr. Kasan's lab section table content. They just need to go to the labs and find it. So that's straightforward. Okay, so but anyway, next things. So we got that this part, and we will have M is less than 0.5 volt per ms, and our peak volt is 10 volts. Okay, so that means our FM is okay. Then you just need to do some unit converting, and you know FM is less than 7957.74 hertz. That means our FM is less than 7.958 K hertz, right? Okay, so we got 2 values. We got the closed loop, okay, the bandwidth one. Obviously, we choose the smaller one, so that's the effective one. Okay, so 7.958. So just keep that in mind. 7.958 kilohertz is the one that we need. Okay, now let's go to the lab. Okay, so we will need the function generators. We will need the scope. We need the THD. Sorry. Yep, this door. Okay, so our THD, everything is here. Then we need to go to our okay, so our outcome is here, and also our resistor, obviously. Basic resistors. What we need, okay, just one of that, and we can duplicate it. And also the source, power source. Okay, I'm going to connect it. So this will be 10K, and this will be 10K. Here. Okay, our load is going to be here. Put input. This is 1000K. Okay. I just try to make it look better, but it doesn't really matter. Okay. Okay, and our input is sorry, load is 10. And the load, we're checking it 100 millivolts. Okay, peak, and the frequency will settle down later. We also need that from here. They could using VCC or VE to do it. So like this one, okay, VCC, VDD, VE, those things is possible to do it. But I will just show the basic way. So really, there's no wrong on how to do it. Obviously, whatever you taught students is the way it goes. Okay, so it's just because it's the same, so it's really no difference. Just make sure they don't reverse the polarities as you guys did in the actual lab before. We all know that when you reverse the polarity, the worst case it can happen is actually the outcome will goes right. And that's will not be so good. Sometimes it even catch fire. So it's kind of dangerous. Just don't reverse the polarity. And the important thing about the reason I want to have this video recorded is this XDA. So again, you find the distortion analyzer, okay, and when you click it, it say THD on there, and they say XDA. Connect this to the output part, output channels, okay. Now we can do the analysis. All right, so I'm just going to set the color for the output be blue color, the input be green color. Remember, we need to test our conclusions. So if it's correct, our FM, we should have this result. We should get this result. So 7.958 kilohertz. is where the limit is. So let's test for 6K to see if we have the expectation result. Okay, when you set the input frequency to 6 kilohertz, on the THD side, you click the THD box, okay, just double click it. You will see this, and you do the same thing by keying 6 there, okay? So you will have the numbers like that. And obviously the scope. Okay, so now let's click running. Just leave for 1 or 2 seconds, you see the number will settle. Now what we have 2.758%, okay? So for the distortion part, we get so now for 6K hertz, our THD is 2.758%, okay? And then we need to know our VO peak output. Okay, what is the VO peak output? Obviously, that's pretty straightforward. You go to the scope, okay, minimize a little bit. Remember, we say what is the green? Green is the input, blue is the output. So we only need to look at the output. So now we can do a trace for channel B, okay, and then all you need to do is go to Ymax, and you can see it. What's the number? 7.907. So we get VO peak for 7.907, 7.907 volt. Okay, remember to do the what's the minimum peak we're supposed to get under 3 dB situations is 10 divided by root 2, which is 7.07 volt. Okay, so we haven't got lower than that, so that means 6K hertz is good. Okay, remember what I'm doing here is just a testing. Students don't have to do this part. Okay, students do not need to do this part. All they need to do is they're going to test directly for this number, 7.958. So maybe saying they can do it for 7.9K hertz. Okay, as long as this is satisfied, then that's fine. Now, when we go to 7.9, okay, so let's do 7.9K hertz. Okay, and we put here. So student will have to find out what's the actual numbers. It may not be 7.9, it may be a little bit lower or higher. This really depending on many factors. See, as I can see it here, 3.632 is over it. So this definitely not going to be the one. Unfortunately, it's over 3.5. So we need to give something lower. Say we go 7.5. Okay, 7.5. So there's a lot of try and error student need to do it here. Okay. So I go 7.5, you see it's 3.48. Okay, so it's not bad. So now I go 7.6, 7.6, okay. 3 points. So we can see it's between that. So let's do 7.55. You know, if students just stop at 7.5 or something like that, it's okay. You don't have to go picky on this. Just my personal feeling is like that. That's good enough. So maybe 7.52, I guess. So 7.52 is my limit on the THD part. Okay. Now let's looking at the output. Obviously, output is very important. We're going to trace channel B and goes to the max. So our result is 7.99934. Okay, so this is not acceptable because as you can see it for 7. What's the value? 7.52K hertz, 2K hertz. My VO peak is, sorry, let me write it quick. My VO peak is equal to VO peak is 6.934. So my VO peak is 6.934 volt. My THD is My THD is 3.4993, 3.493. 3.493%. This is fine, but this is not okay. So there's a problem for this one. So we have to continue lowering down our frequency. Obviously, you know, it's somewhere between 6 above and between 6 and 7.3. So we know 6 is fine. We know 6 kilohertz is okay. We know 7.52 kilohertz is not okay due to the VO peak. So VO peak is not okay, but THD is fine. And this one, so both are okay. Okay, so they are both okay. So we just need to find the value in between. So because we don't need to worry about THD will continue lowering down. So from now on, when we lower down the values, we all have to check is just the peak. Now let's see it. Okay, so now let's see this one. Okay. Okay, so again, we need to chase channel B. Okay, go to Ymax 7.01. So this is still lower than because we need 7.07, right? So the value still need to be decreased. So 7.3K, let's say that. Okay. Okay, again, trace channel B. Okay, let's see what's that number. Okay, I have 7.07. Okay, very good. So this should be the one. Okay, now let's change this one to the same value just to double check, make sure the THD is also correct. So my THD stop at 3.406. My peak, just make sure, because every time when you run it, there's a little bit difference. So Lab3 is actually a little bit more works for student to do it. But anyway, so when I test 7.3, as you can see it, I have the, let me just cut it. Okay, so everything, cut it and paste on the note. Okay, so now, as you can see it here, okay. Okay, so let me just, okay. Just make sure this goes to the smaller one. Okay, as you can see it here, for the VO, so VO output peak, okay, is equal 7.074 volt, and our THD is 3.406%. So they both satisfy, and our frequency is 7.3 kHz. Okay, so then student will say, okay, so based on the pre-lab, he gets 7.958, but when he actually did the simulations, so on pre-lab, I get 7.9 kHz, but on the lab, on simulations, okay, the lab, I will get 7.3 kHz, okay, and that's how it is. So obviously, as you can see, the better slew rate is, so the higher the slew rate values, the better the outcome is. But one thing you can remind students to consider is the price of the outcome. So I'm going to share you the page, which this is the electronic store I went. So when you buy two 741 outcome, it's costing 2.5 for two package. So one of them is $1.25. When you buy 318, it costs you $2 per APAM. So, well, which one is better is really up to your choice. When we do the design, if you see the designing for 741, you will need to use two of them. For 318, you will actually only need to use one of them. So on the price base, actually 318 is cheaper because you only need one. But it may, depending on where you get the things from, okay, because the supply, you can see the supply number is different. See, 318 is not that many compared to 741. 741 always have more supply, and it's easier to get it. You know, there's a lot of factors, so you can tell students to consider those things. It's a lot of things to think about it. And the other thing is, if you want to show them, so let me just go to this part, okay? And I'm going to take away my background. So. Okay, so give me 1 second. Okay, so hello everyone. So I'm just going to show you. So this is the 318. Okay, so when we actually go back, so at the and Ian, they both know this, but I'm pretty sure Daniel, you also know it. So this is the 318s. Okay, so well, when they connect it, they obviously know it. So as you can see, there is a dot there. So from the dot point, okay, the up. So when you put dot on this side, the upper one is what ping 1, ping 2, ping 3, ping 4, and down goes back to here 5, 6, 7, 8. So it's important students know which one, which pin they should connect, especially the power supply. 4 to the negative, 7 to the positive, 6 to the output, 2 and 3 negative and positive. So those things they supposed to know it. And when we actually go back to the real lab in the future. So that's everything I want to say it about lab number 3. If you guys have any questions, let me know it. Okay, feel free to let me know it. I will also share the circuit with you guys. Okay, good luck.